All right, let's try a new challenge. Can we make a regular lattice decagon? All right, can we make a regular lattice decagon? Okay, so rather than using GeoGebra like we did with the octagon, let's think about the patterns that we learned with the octagon and apply them here inductively. So what did we need to make a regular lattice octagon? Well, we needed to be able to fit all of the line segments onto a four-sided frame and then push them in from the corners. So let's give ourselves a four-sided frame. With the octagon, the way to maximize that polygon was to use a square, but it can be a four-sided shape. It needs to be a four-sided shape with perpendicular lines and 90-degree angles. So it can be a rectangle or a square, which is a special type of a rectangle. So what do we know about a rectangle? Well, this side, oops, here we go. This side needs to be the same length as this side, and this side needs to be the same length as this side. Okay, so what is our perimeter for a decagon? Well, we've got 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. And what is that? Well, we've got 10 plus 1, which is 11. 9 plus 2 is 11. 8 plus 3 is 11. 7 plus 4 is 11. And 6 plus 5 is 11. So we've got 11, how many times? 5 times is 55. Okay, so how can we fit a perimeter of 55 onto four sides of a rectangle? Well, rather than just plugging in numbers until we get it right, let's think about the concept of what numbers are. Let's break it down into like one of the simplest categories that numbers can be grouped into. Okay, how about even and odd? Let's see if there's a pattern with how even and odd numbers work. So what are the possible combinations? Let's see. If this side ended up having an even total, this side would have to have an even total. And an even number plus an even number is an even number. Okay, so this side would, the combination, the sum of those two parallel sides would have to be even. Okay, let's try another combination. If this side's odd, this side has to be odd. So an odd number plus an odd number is an even number. If you didn't know this, you can experiment with it yourself and see this rule that has been proven by mathematicians. Okay, so what's another possible combination? Well, they could be opposite. We could have this side be even, and this side be even, and then this side be odd, and this side be odd, but we'd still end up with the same basic thing. So what are the combinations here? Well, it could be just like this picture, which would mean that these two sides added together, an odd plus an odd is an even, and then an even plus an even is an even. So the whole perimeter is going to be even plus even. And that would mean the perimeter has to be even. Okay, well, what if let's see, what if it's all odd? So let's say these are odd. Well, an odd plus an odd is an even. And an odd plus an odd is an even. So again, we've got even plus even must be even. So the whole perimeter would have to be even. Okay? So what if it's all even? Let's just put an E for short. So an even plus an even is an even, and an even plus an even is an even, and an even plus an even is an even. So what did we just prove? That the perimeter of a rectangle has to be even. This holds true for any rectangles, not just in regular lattice polygons. So, what do we know now? We know that it has to be even. So, can we have a regular lattice decagon? We just calculated that the perimeter is 55. Can we fit those segments around a rectangular frame? No. So we can not have a regular lattice decagon. Okay, well, let's try another one. What about a regular lattice hexagon? That means it has 6 sides. So we know the perimeter must be even. So let's see. We've got 6 plus 5 plus 4 plus 3 plus 2 plus 1. Okay, so what's that total? 6 plus 1 is 7. 5 plus 2 is 7. 4 plus 3 is 7. So we've got 7 times 3. And that's 21. 21 is odd. So we can not have a regular lattice hexagon. Okay, what pattern are we seeing? What do we need to create a frame with perpendicular angles? We need an even perimeter. I wonder if there is a simple rule that will allow us to quickly know if we can make a regular lattice polygon or not without having to add the perimeter to see if it is even. Well, let's look for a pattern. All right, when an 8-sided regular lattice polygon had a perimeter of 8 plus 1 times 4, and that was 36. All right, a decagon has a perimeter of 10 plus 1 times 5, which was 55. And the perimeter of a hexagon, we did it up here, and we did 6 plus 1 times 3, and that was 21. Okay, so what's the formula here? Is there a pattern so that we could make a formula? Okay, well, it looks like, let's see, let's put a little subscript here. So like the perimeter of an 8-sided polygon, perimeter of a 10-sided, perimeter of a 6-sided. So let's say a perimeter of an n-sided polygon would be what? N plus 1 times, what are we multiplying it by? Let's look at our examples here. So an octagon was multiplied by 4. A decagon was multiplied by 5. And a hexagon was multiplied by 3. So what is that? It's half of n over 2. So that's our perimeter. That is a formula for a perimeter that would allow us to see if it's even or not. Well, could there be an even more specific rule that would allow us to save even more time? Currently, we would have to use our perimeter formula for every value of n and see which ones are even. Could there be a faster way? All right, so I've written over here on the left the two things we know that we need for regular lattice polygons. Okay, the perimeter needs to be even, and then we have our perimeter formula. Well, let's see if we can find anything else. So we have done hexagons, octagons, decagons. Let's try an 11-sided polygon. Okay, what would that look like? So P, the perimeter of an 11-sided polygon would be 11 plus 1 times 11 over 2. Well, 11 over 2 is going to give us a fraction. It's not going to give us a whole number. So that will not give us an even number that we can put around a rectangular polygon, a frame, a rectangular frame. So this will not work. Okay, let's try it 12-sided. 12 plus 1 times 12 over 2. All right, and we're going to get 13 times 6, which is 78. That is even, so yes. We could make a regular lattice polygon with 12 sides. All right. So let's think about what we just saw with 11. If we put 13 over 2, that would also give us a fraction. So now we've just learned that only even-sided polygons, only polygons with an even number of sides can make a regular lattice polygon. So now we know that the number of sides must be even. But that only cut out half of all the numbers we'd have to try. We still would have to plug in all the even numbers to see. I wonder if there's any more of a pattern. So let's try another even polygon. Okay, let's try P14. So we'd have 14 plus 1 times 14 over 2. And that's going to give us 105. 15 times 7. Oh, no. That's an odd perimeter, and that could not give us a regular lattice polygon. Okay, let's try the perimeter of a polygon with 16 sides. So it's 16 plus 1 times 16 over 2. So that's 17 times 8, and that gives us 136. Yes, the perimeter of a 16-sided polygon is even, so we could use it to make a regular lattice polygon. Okay, what about 18? 18 plus 1 times 18 over 2. That's 19 times 9, which equals 171. No, that's odd. Okay, so there is a pattern here. So it's looking like every other even number can give us a regular lattice polygon. Can we find a logical reason for that, which could point to a general rule that we could prove to be true? Well, when n is 12, when the number of our sides is 12, our formula results in an odd number times an even number. So we had 13 times 6. Okay? And that gives us an even product. Okay? So let's move this idea down here. So an odd number times an even number gives us an even product. Okay. What about with 14? So we had 15 times 7. We had two odd numbers. An odd number times an odd number gives us an odd product. And that will not work. So this will consistently happen. This means that every other even number are the only ones that will work for a regular lattice polygon. So is there a way we can describe every other even number? Well, if even numbers are all multiples of 2, so even numbers are all multiples of 2. 2, 4, 6, 8, 10, and so on. So what would give us every other multiple? So we want 8, so then 4. We know 8 works, so then 4 would work, and so on. What would that be? Wouldn't that be multiples of 4? Okay, let's see. We know that 8, 12, and 16 all will create regular lattice polygons. And we see that the ones that did not make lattice polygons, 6, 10, 14, and 18, are not multiples of 4. So that works. Now we only need to ask ourselves, if a value of n is a multiple of 4. So now we know that the number of sides must be multiple of 4. So can we make a regular lattice polygon with 400 sides? Can we divide 400 by 4? Yes. So yes, we could. That's it. We don't have to plug in anything to the formula, calculate anything. We know the answer is yes. Can we make a regular lattice polygon with 414 sides? No, because you can't divide 414 evenly by 4. So we used inductive reasoning and finding patterns to make future solving of regular lattice polygons a lot faster and easier, because we saw the patterns and we made a general rule which will apply to all regular lattice polygons.